All right, suppose R is a relation from A to B, and S is a relation from B to C. So the picture we have in our minds is got three sets, A, B, and C, with a relation R from A to B, and a relation S from B to C. And then we want to show these two sets are equal. The inverse of S composed with R equals R inverse composed with S inverse. And all right, well, what does an element of the left-hand side look like? First of all, let's imagine we have an element little a in A, an element little b in B, and an element little c in C. And an element of S composed with R. Remember, R comes first, just like with functions, you do the one on the right side first. And so that would be something of the form ordered pair AB, right, which we could represent by an arrow from A to B. And then something in S looks like maybe ordered pair BC. Okay. And then if we want the composition, then we would know that if those two are in R and S, then this one, AC, is in the composition. And then we're going to take the inverse of that, and so that's going to just change the direction of the arrow. So we would get that CA is in the left-hand side of my equation. Well, what does an element of the right-hand side look like? First, we're supposed to take an element of S inverse, which would be something like CB, and compose that with an element of R inverse, which would be something like BA. And when we compose those, we get the same thing we got before, CA. All right. So this sure seems like it ought to be true, but we're not exactly sure, which sort of ABs and which BCs are involved, and what these compositions might look like in terms of the quantifiers that are involved. So we should prove this thing. We've had these givens that R and S are relations between the appropriate sets, and we want to prove this equality of sets. So we want to prove that, well, for all P is in the left side if and only if P is in the right side. We're going to be a little bit sloppy or concise, let's say, that's a more positive word, and go ahead and realize that anything in either of these sets, these are both relations from C to A, okay, if you trace through the definitions. And so an element of either of them is going to have to be an ordered pair of this form. So let's go ahead and say that CA is in the left side if and only if CA is in the right side. And there's an implied sort of for all A and for all C out front here, which we will not bother to write. All right, so we can do this with, well, probably in a lot of ways, but the two ways I'm going to show you are a chain of if and only if statements, and then a chain of equalities of sets, okay? Which is just basically the same as the first one, but a little bit more writing, okay? So probably I like the first one better, but I want you to see both. So, all right, the first thing I'm going to do is sort of an explanation of why I'm using CA as sort of my arbitrary element instead of just P. Okay, and it's because, as I already mentioned, these two sets are both relations from C to A, so their elements are in C Cartesian product A, right? So they're all ordered pairs with C and C and A and A. All right, so CA is in the left side. Well, what does it mean to be in the inverse of a relation? It means that if you change the order of the two coordinates, then that's in S composed with R. And then to be in the composition, that means there exists some B in the middle set such that AB is in R and BC is in S, right? So you can get from, right, so AC is in the composition if there exists some B in the middle set capital B such that AB is in R and BC is in S. Then you get that this is in the composition. Okay, and then AB in R is the same thing as BA being an R inverse, and this is the same thing as CB being an S inverse. The reason I'm rewriting them that way is because I know where I'm trying to head, right? Something about R inverse and S inverse. And then, well, the problem here is that the two, you notice when I did this definition, the two middle coordinates were B, right? Well, the two middle ones are not the same anymore, okay? But if I just use sort of commutativity with the and symbol here and switch the order of these two statements, then the B is in the middle again. And so I get basically the first thing C with the last thing A is an element of well, R inverse composed with S inverse, right? Remember, the first one, which in this case is the S inverse, goes on the right, and the second one goes on the left, just like with functions. Okay, so we end up with a CA in the right-hand side of our original inequality, and we're done. Okay. Now, maybe instead of talking about what this element is as sort of the statement that we are refining, we might just want to deal with sets. So let's just sort of start with the left-hand side of the equation and then write out the definition of that set and work with it, and eventually basically working with the elementhood tests here, and then arrive at the right-hand side set. Okay, so this inverse is the set of all CA such that AC is in S composed with R, and this is going to track what we did up here, right? That means that this existential statement is true. There exists a B in the middle. And then we can rewrite in terms of R inverse S inverse, and we can switch the order, and that means that CA is in here. And then this is kind of funny. The set of all CA such that CA is in there is that set, right? So that's kind of like saying, you know, the set of all letters named X is the set of just X. Okay, well, maybe not, I don't know. But it's, anyway, it's that. Okay, so those are two different ways of doing this proof, and I like the first one better, but you can decide what you like.